Okay, so good day. Ang topic natin dito sa video is beam deflections. Okay? So, syempre bago tayo simula, introduction muna tayo and pakita natin yung magiging flow nitong topic na to. Kasi this will be a series of videos kasi iba-iba yung methods na pag-aaralan natin dito. Okay? So, pag-aralan muna natin kung ano ibig sabihin ng deflection, bakit siya mahalaga. So, sabi dito, deflection is caused by many sources such as loads, temperature, construction error, and settlements. Okay? Pero dito sa mga methods na gagawin natin, deflection will be caused by loads lang. Okay? No temperature, no construction errors, okay? No settlements. So it is important to include the calculation of deflection into the design procedure to prevent structural damage to secondary structures. Okay? Kasi diba ang kinocompute natin sa structural analysis is yung internal forces, axial, moment, and shear. Okay? Ngayon, sinasama rin natin ang deflections. Bakit mahalaga yan? Kasi kapag yung deflections ay naging sobra, okay, more than the allowable provided by the code, okay, o yung provided by dun sa design, magkakaroon ng damage dun sa secondary structures. For example, halimbawa, meron tayo ritong beam, okay, natin block. Then, meron pa tayong isang beam dito sa baba, okay. Then, let's say, natin block yan. Then, let's say, sa gitna ng dalawang beam na yan, ay meron tayong wall. Okay, let's say that's a glass wall. So, syempre, etong glass, brittle yan. Okay, so kapag nag-deflect ng malaki yan, mababasag yan. Okay, so, kung magde-deflect ng masyadong malaki yung beam mo, okay, yung beam mo sa baba, or yung beam mo sa taas, or kung both silang nag-deflect ng masyadong malaki, ang mangyayari sa glass mo ay, syempre, mababasag yan. Okay? Kaya natin nililimit yung deflection sa mga structural members natin is para hindi ma-damage yung secondary members na nakalagay sa kanya. At isa pa, ito ay may kinalaman din sa tinatawag na serviceability ng structure. Okay? Kasi ang ating pinagbabasihan ng safety is unang-una yung strength. Okay? Kailangan yung mga structures mo ay kayang pasanin yung mga loads na naka-assign sa kanya. So, that is strength of a structure. Pero bukod doon sa strength, kailangan din nating tignan yung serviceability. Kaya pa bang mag-serve ng structure? Pwede pa ba siyang magamit? Kasi kung yung beam mo ay sobrang nakalundo na, ibig sabihin may impending na na-failure yung structure mo. Okay? O syempre, sa mga occupants, hindi yun komportable na yung nakita mo yung beam ng bahay mo ay nako, ang laki na ng deflection, malamang aalis ka na ron. Okay? Kasi isipin mo, ay teka, baka mag-fail na itong bahay ko kasi ang laki ng deflection. Okay? So, ibig sabihin, kapag masyadong nag-deflect yung isang member, hindi na siya pasado sa serviceability. Okay? Pwedeng kaya niya pang pasanin yung mga loads, okay? Kaya pa ng strength niya. Pero dahil sobrang lumundo na siya, hindi na siya pasado sa serviceability requirements. Okay? Yun ang importance kaya kinocompute natin ang deflection. Tandaan, serviceability, ang kinocompute ay deflections. Okay? Sa strength, ang kinocompute ay internal forces. So, you have axial, shear, and moment. Okay? So, yun. So, next is yung deflection calculation methods. Nga pala, bago tayo mag-proceed dyan sa methods, banggitin muna natin yung assumption na dito sa topic na to, sa deflections, yung ating mga beams ay kino-consider natin na elastic. Okay? Elastic. Pag sinabi natin elastic o pag nag-refer tayo sa property na elasticity, ibig sabihin kung halimbawa ito yung bagay, object, in-apply mo ng load P, okay, load P, edi syempre ang mangyayari dyan is magkakaroon siya ng deformation. This is basic sa strength of materials. Tama? Tapos, kapag inalis mo yung load P na yan, when those applied loads are removed, okay, P, so forces, nagkaroon siya ng deflection. Pagka inalis mo yung mga forces na yan, babalik siya sa dati niyang shape. This is elasticity. Okay? Ibig sabihin, the deflections are present as long as the loads na nagkakos ng deflection yun are present din. Pag nawala yung deflection, pag nawala yung forces applied, then wala na rin yung deformation. That is elasticity. Ang kabaliktaran ng elasticity ay plasticity. Okay? When you say there are plastic deformations doon sa beam, ibig sabihin, halimbawa, masyadong malakas yung pagkakahatak mo doon sa isang object. Okay? In-apply mo ng tensile load P. Okay? Ngayon, pagka in-apply mo na masyadong malakas sa tensile load P at lumagpas siya doon sa kanyang elastic region, edi plastic na siya. Ibig sabihin, those deformations, na permanent deformations, o yung deformations na yun ay plastic na and those are permanent. Hindi na siya babalik sa dati yung shape. Okay? So, masyado nang nasaktan yung iyong object, so hindi na siya babalik sa dati yung state. So, yun. And kung naaalala nyo, yung stress-strain curve, I think this is discussed doon sa strength of materials. So, stress-strain curve is that curve showing the relation between stress, sigma, and strain. Okay, so alam ko ang pinakita sa strength, o ang pinapakita kadalasan sa strength of materials ay yung stress-strain curve ng bakal. Okay, so sabi, it will be linear for for a while, tapos there is a yielding point where kapag in-increase mo pa yung stress, okay, hindi na siya magiging linear yung relation ng stress and strain. Di ba ganito yun? And this is the rupture point. Okay? So, ang elastic region dyan ay eto lang. Okay? Ano, di ba? This is Hooke's law. Di ba ang sabi sa Hooke's law ay straight yan. Di ba ang equation ng straight line is y equals mx plus b. Di ba? Ito yung Hooke's law eh. Di ba yung y equals mx, ibig sabihin straight line. Okay? Pagka b is equal to 0, ibig sabihin then the line is passing through the origin. Y natin is stress. Sigma equals m natin is yung slope ng line which is represented by the modulus of elasticity ng material. Okay? Tapos, yung ating x ay yung, teka, ba't mali yung symbol natin dito? Ay, shucks. Okay. Ang symbol sa strain ay epsilon. Okay. Okay, so, yan. Y equals mx. Y, which is stress, equals m, which is yung slope ng line, straight line, and x is strain. Okay? Ito yung sinasabi sa Hooke's law that stress is directly proportional to strain. Okay? So, itong portion na to where Hooke's law is valid, ito yung tinatawag natin na elastic section. Okay? So, as long as yung stress mo ay hindi lalagpas dito sa may point na yan, then, yung object mo, ibabalik pa sa dati niyang shape pagka tinanggal yung load kasi nga elastic pa. Pero once na tinaasan mo pa yung stress na in-apply mo doon sa material, then mag-i-strain na siya permanently. Ibig sabihin, siya ay nasa plastic region na. Okay? All the formations are now permanent. Okay. So, yung introduction natin. Tandaan mo na sa topic natin ngayon, dito sa series of videos na to, ang assumption natin is yung beam is elastic. Okay? So, yun. Then, pag-usapan na natin ang calculation methods o yung mga methods na gagamitin natin for calculation of deflection. Okay? So, first set, we have geometric methods. Ibig sabihin ng 3, we will be covering 3 geometric methods. Okay? 3 different geometric methods. So when you say geometric methods, these are based on a consideration of the geometry of the deflected shapes of structures. Sa geometric method kasi, as its name implies, nagbe-base siya sa geometry ng beam. Okay? Paano ba natin nalalaman yung geometry ng beam? 'Di ba dun sa ano natin sa tawag diyan, sa mga lesson last time, let's say we have a beam here. Okay, beam ulit. Tapos, let's say ang moment diagram niya. So, ganito na lang. Uniformly distributed load. Okay. Basta ganyan. Uniformly distributed load siya. Ang moment diagram niya is, let's say, ganito. Yeah. That is its moment diagram. Okay? Since the moment is all positive, okay, when your moment is positive, ibig sabihin nakangiti yung beam mo. Ibig sabihin, your beam is smiling throughout its length. Okay, ito yung elastic curve niya. Familiar na kayo sa term na elastic curve, ha? Siyempre, meron na tayo niyan. Ginawa na natin yung nakaraan. Itong shape ng elastic curve na to, ito yung tinatawag natin na qualitative shape, di ba? Qualitative deflection o qualitative deflected shape ng structure. Okay? Pero hindi natin dyan kino-compute yung value mismo ng deflection delta. Okay? So, ano bang pinagbabasehan natin ng qualitative deflected shape? Which is, walang nang iba, kundi yung moment diagram lang. Kaya, dito sa geometric methods natin na pag-aaralan, sa tatlong methods na to, we are heavily dependent on the moment diagram or the moment equation of the structure. Okay, kailangan natin makuha yung moment. Yung shear, hindi ganun ka-significant katulad ng moment. Kasi diba dun sa strength of materials, we have that equation na rho equals EI over M. Okay? Ano ibig sabihin nito? Na yung radius of curvature is directly proportional to EI, okay? And inversely proportional to moment. Ibig sabihin, as your EI increases, when your EI is very big, then the radius of curvature of a portion of a beam is big. Okay? Halimbawa, let's consider yung ganito kahabang structure or object. If there are no moments experienced by this object, then there is no deflection. Okay? No moment, no curvature, no deflection. Okay? Ngayon, kapag in-apply natin ito ng moment, M, okay? Pagka in-apply natin yun ng moment, syempre magde-deflect yan. Okay? Yung kanyang deflected shape. Okay, and ito yung kanyang radius of curvature. Oops. Ayan, kung ano man yung radius na yan, that's his radius of curvature. Okay? Ngayon, kapag in-increase pa natin yung moment, okay, same object, pero the moment ay mas grabe. Okay, pagka in-increase pa natin yung moment, ano mangyayari? Eh di mas babaluktot yung beam mo. Okay? Mas ganito yung beam. Okay? Kapag mas malakas ang moment, mas maliit ang radius of curvature. Yun ang ibig sabihin ng formula na to. Mas malaking moment, mas maliit ang radius of curvature. Mas maliit na radius of curvature, ibig sabihin mas baluktot yung beam. Mas baluktot yung beam, ibig sabihin mas malaki ang deflections. Okay? So, ayun. Kaya, we are heavily dependent on the moment diagram or moment equations when ang pinag-uusapan nating method is geometric. Okay? Pero, meron naman tayo isang method na hindi nagbe-base sa moment equations o moment diagrams, which is energy methods. Meron tayo isa na itatake tungkol dyan. Okay? Hindi lang kasi tatlo ang geometric methods. There are others. Pero tatlo lang yung focusan natin. Same dito, hindi lang isa ang energy method. Okay? Pero isa lang ang focusan natin. So, eto yun. Ano-ano ba yun? So, una, sa geometric methods, we have double integration method or DIM. We have area moment method. We have conjugate beam method. Okay? Hindi ko, ang suggestion ko is mag-master lang kayo ng at least dalawa. Bakit dalawa? Kasi para kapag may sagot ka na using one method, double check mo siya using another method. Okay? So, ayun. Pag-uusapan natin yung mga methods na yan sa mga susunod na video. And sa energy method, we have the virtual work method. Okay? Ang ginagamit lang natin is basic of principles of work and energy. So, kung sa statics, umabot kayo sa virtual work method, maiintindihan nyo na maigi. Other methods, three-moment equation and slope deflection equation. Kaya ako siya tinawag na other methods kasi ang focus muna natin is yung mga statically determinate muna. Okay? Pero these methods can also be used to solve redundancies and deflections of statically indeterminate beams. Okay? Pwede rin yan. Pero sa ngayon, ang focus muna natin is statically determinate beams. Okay? As a starter. Ito kasing three-moment equation. This is used to solve deflections and other redundant reactions ng continuous beams. This is specifically made for continuous beams, especially made for continuous beams. And ito ay derivation lang o derived lang from area moment method. So, okay, slope deflection equation is mostly math, DE, okay, integration or calculus. Okay, so doon naman tayo sa definitions. Dito kasi sa deflections, dalawa ang kadalasang hinahanap natin. Okay? Deflection and slope. So, deflection, this is defined as the vertical distance from a point in the beam's deflected elastic curve to its original undisturbed position. Ano ibig sabihin nun? So, syempre, drawing natin. So, gawa ulit tayo ng beam. Okay? So, yeah. Oops. Let's make it black. Syempre, ang elastic curve niyan ay wala, diretso lang. Okay. Ayan. Yeah. Yeah, let's say that's our beam. Ito yung kanyang elastic curve o yung curve o yung line tracing the neutral axis of the beam. Okay? Ngayon, syempre, pagka nilapagan mo ng load yan, yung beam na yan, load P, magde-deflect yan. Okay? And ang elastic curve niyan ay magiging ganito. Okay? Assume lang. Okay? Kasi ang kanyang elastic curve. Okay? Let's say we have this is point A. Okay? The mid span is point B. And point C is a random point dito. Okay, when you say deflection at point A, ito yung distance from the initial position of the elastic curve, kung nun siya ay naka-straight pa, hanggang dun sa position nung deflected na elastic curve. So, this is delta A. Parang mali yung drawing ko. Okay, when you are asked about the deflection at point B, ibig sabihin, ito yun. If this is point B initially, nung wala pang load, and this is now point B nung siya ay nag-deflect na, then the vertical distance between them is deflection at B. Same dito. If this is point C, the original point, and this is point C now, kapag siya ay nag-deflect, then this is delta C. Okay? So, yun ang definition ng deflection dito. Next is yung slope. So, slope, the slope of a tangent line passing through a certain point on the beam. Okay? So, kunin ulit natin tong elastic curve ng beam na yan. Okay, let's redraw. Panindigan na natin yung ayan. Okay. When we say deflection at point A, but this is point A, tama? This is point A. Sorry, when we say slope pala at point A, may tangent line dyan. Okay? Tayong tangent line. medyo usog natin. Yan. Okay, let's say that's tangent line A. Tangent line passing through point A. Pag sinabi mong slope at point A, yun yung angle, horizontal angle. And this is slope at point A. Okay? A negative slope means the tangent line at that point is baba. Okay, ibig sabihin, you have a clue na yung beam mo sa point na yun is nakangiti kasi ang tangent line niya. O, tawag dyan, pababa. Meron din palang tangent line na pataas kapag ka nakangiti yung beam. Anyway, may idea ka kung ano yung direction ng beam mo at that point. When you say slope at point B, then this is point B. Then, kunin mo yung slope ng beam dyan. Let's say that's the slope of the beam at point B. Okay? Then, kung ano man yung angle that it makes with the horizontal, okay? This is slope niya at B. And ganoon din, same. Kapag kinuha mo yung slope at point C, then you are getting the angle formed by the tangent line passing through C to the horizontal. That's slope. Okay? So, yan yung karaniwang hinahanap natin dito sa topic na to. It could be radians or degrees, depende. Okay, so next definition is flexural rigidity or EI. Okay? O yung pinakita na nga natin kanina dito sa may formula na yan, EI. Dito, kapag malaki yung EI, malaki yung radius of curvature. Ibig sabihin, hindi siya masyado nakabaluktot. Okay? So, this is defined as the force couple required to bend a fixed non-rigid structure by 1 unit of curvature. Or ito, mas gusto ko itong definition na to, which is mas simple, as the resistance offered by a structure while undergoing bending. Ibig sabihin, kapag mas malaki ang EI, ibig sabihin, mas malaki ang resistance against bending. Yun lang ang ibig sabihin na. Mas malaki ang flexural rigidity, mas mahirap siyang i-bend. Ibig sabihin, the deflections are less. Okay? Pagka maliit lang ang flexural rigidity, ibig sabihin, medyo mas malambot yung beam mo. Okay? So, bawa ganyan. You have a beam of this cross-section and you have a beam of this cross-section. Okay? So, syempre, ang EI neto, EI1, EI2, if the EI, if yung EI ng una is mas malaki, ibig sabihin, this is harder to bend. Ibig sabihin, this will have smaller deflections kapag parehas mo silang in-apply sa same load. Okay? Yun na ibig sabihin ng EI o ng flexural rigidity. At dito sa topic natin, siguro each method magbibigay ako ng 4 na examples and same examples lang gagamitin ko para ma-verify natin na pare-parehas yung sagot kahit anong method ang gamitin mo. Okay? So, you have example 1, which is ito. Okay, a cantilever beam na may concentrated load, tas may UDL sa dulo. Okay, questions. Example 2, simply supported beam na may naka-overhang dun sa kanan. Tignan nyo, kadalasan laging given na yung mga EI. Okay, ito given na rin. Example 3, wala tayong numbers, so we will be solving naka-letters lang. Okay, so this is a cantilever beam ulit na may uniformly varying load. And take note na from example 1 to example 3, we are having a prismatic beam. When you say prismatic beam, yung cross-section niya is not changing. The cross-section does not change throughout the length of the beam. Ganun din dito, the cross-section is not changing. So, ganun din dito. So, nagbigay ako ng isang example ng non-prismatic beam. Okay, sabi mo, non-prismatic may change sa cross-section. Okay, so, eto, A to B, medyo mapayat siya. So, M. Okay, and B to C, medyo mas mataba siya. So, mas mahirap i-bend dito sa may BC kumpara sa AB. Okay, so this is an example of a non-prismatic beam. Okay, so that's the end of this video. introduction lang and I will upload ulit later para dun sa unang method natin which is the double integration method or baka unahin ko i-upload yung area moment method. So, I'll upload later. Okay, so see you.